I'm in, so as I was saying, I'm in another city, and all the work that we've done is on another computer in my home city, and I haven't been feeling well, and I haven't had a chance to get back. So in order to get back to where we were, to get to day 6, I basically have to start from scratch. So you're going to watch me go through this in real time as I would do it if I was working on my own. Okay. Um, okay. So let me just do this. Um, and we have the data file here. Uh, we have the data file here, and I'm going to go through all the steps just so we can get caught up. So as you can see here, we have all of these variables, and I haven't computed anything. So now let me just run descriptive statistics. Because we already know what what the research questions are, and so on and so forth. Right. So we already know that this is a relationship question, prediction question, difference question. And we already know that we're going to run a bivariate correlation, a multiple regression, and a one-way ANOVA. So for research question 1, age is related to optimism. We're going to run a bivariate correlation. We're going to run a multiple regression to address our optimism and self-mastery predictors of perceived stress. And we're going to run a one-way ANOVA to evaluate if there are significant differences in optimism scores between the younger, middle-aged, and older participants. All right. So I got to get this data file up to spec because none of the variables that we created have been created. This is a different file. It's the same file, but it's not clean. So let me just do a little stopwatch here. Stopwatch. So you'll be able to see basically how quickly I can get this done. Okay, so let's start. Frequencies. So we're going to do sex all the way down. Okay, so it looks like, okay, we're down to child. Okay, so we've got to remove child, this one for child. So I'm going to go to the data file. Going to be very quick. Sort this ascending, and I'm going to remove this respondent.
Jacob, we are not able to see the screen.
Oh, okay. I'm sorry. All right, there you go. There you go. Sorry about that. Okay. So as I was saying, we know that we're going to run this, but if you look at the data file, this data file is not the same data file that we've been working on because I'm in a different city. So I had to start basically from scratch. So just let me get caught up for a second. Let's see. So I'm just going to run these descriptive statistics again and make sure. Okay, so we're 414. Okay, that's good. Now I've got to compute. I've got to recode these variables. And I've got to do that really quickly. So we've already done that. So now I've got to do these recodes. All right. So I'm gonna copy this into syntax so that I'll know what I'm doing. All right, so the first one that one of the ones that we don't have to life satisfaction, there is no, so I'm just going to compute life satisfaction really quickly. So life satisfaction is just total scores, so we're just going to compute that really quickly. So compute life stat total equals sum of this to this, paste, and I highlight this and run it. All right. So now we have life satisfaction total. All right. So now we're going to compute the reverse codes for optimism. So 2, 4, and 6. Recode into different variable. Optimism 2, 4, and 6. 2, 4, 6. So this is going to be opt to reverse, opt for reverse, opt 6 reverse. Okay, and let's see. 1 is, make sure, 1 to 5. Okay, 1 is 5. 2 is 4. 3 is 3. 4 is 2. And 5 is 1. Paste. Highlight this. Run it. All right, so, and then we've got memory, got mastery. So I'm going to do perceive stress next. So I'm going to do perceive stress next. So this is going to be PSS 1. Okay. So PSS 4, 5, 7, and 8. So essentially what I'm doing here is I'm taking the same codes because it uses 5, and I'm saying PSS 4, PSS 5, PSS 7, PSS 8, 4, 5, 7, and 8. And then this is going to be PSS 5, PSS. This is PSS 4, PSS 4, PSS 5, PSS 7, PSS 8. Okay, I'm going to highlight this and run it. Okay, so I'm going to look here. You know what I did? Okay, so here's what I didn't do. So this new variable is going to be PSS. So now we're going to, okay, so let me just check those two to make sure that there's no missing values. Uh, okay. Okay, great. No missing values. All right. So, okay, so I'm almost there. So I've got one more to do. And this one is mastery. And we have, it's a 1 to 4 scale. It's 1, 3, 4, 6, 7. Okay. So this one's mastery, and mastery is MAST. All right. So we're going to take this, copy it. And then instead of 1 to 5, so it's 1 to 4, 2 to 3, 3 to 4, 1, 2, 3, and then 4 to 1. And we're going to delete that one. And then it's mastery 1, 3, 4, 6, 7. So MAST, MAST 1, MAST 3, MAST 4, MEST 6, MEST 7. And this becomes MEST 1, MEST 3, MEST 4, MEST 6. And then we're going to do one more. Take off the period. MEST 7. All right, so let's 7. 1, 2, 3, 1, 2, 3, 4, 6, 7. 1, 3, 4, 1, 3, 4, 6, 7. 1, 3, 4, 6, 7. 1, 3, 4, 6, 7. Okay, we highlight that. Okay, so then we're going to run a quick frequency to make sure there are no missing for mastery. Okay. All right, great. All right, so good. All right, so we're almost there. So now I just have to compute. Okay, so the computations. So, okay, so code opt. Okay, so compute code op. That's why when I was showing you before, so we're gonna say toad op. Reset this, put in this control V, tote optimism, and it's going to be, let's see, what is this? This is a sum. Sum. So this is reverse. This is reverse. This is reverse. right? Let's just check it and make sure it matches 2, 4, 6. All scores added. So 0, 6, 2, 4, 6. Okay, so 2, 4, 6. 1, 2, 3, 4, 5, 6, and then it's reverse. 2, 4, 6. I'm gonna click paste. Comma. Oh, no, didn't have a closed parentheses. All right, click paste. Total optimism. Click paste. Highlight this. Run it. And then we're going to check it. Okay. Okay, that's fine. 7 to 30. Okay, we're good. All right, so now the next one that we're going to do is T mastery. So we're going to call that T mass. Copy. And what we're going to do is we're going to make this even simple. Copy. We're going to call this T mast. Oops. So T mast. And T mast has all of these in it. So we're just going to substitute all of these and then just put a T mass REV, 2 T mass REV, or REV, mass 6 REV. Let's see, I thought mass only had, yeah, it's got 7. Okay. Yep. Okay. That's fine. So 1, 2, 3, 4, 5, 6, 7. Okay. Highlight this. Let's make sure. Yep. All right, that's fine. Uh-oh, wait a minute. Oh, didn't change that one. It should be REV because there's no matching one. So total mass REV. 1, 2, 3, 4, 5. Oh, here it should be REV. All right, so we run it. All right, it ran. So now we're gonna test it. Hide this and run it. Okay, great. All right, so we have everything that we need. So I'm just gonna do something really quick. Just gonna check this really quick from the Cronbox Alpha, scale item reliability, and then we're gonna do life satisfaction because that had no, it had no items that needed to be redone. So I'm just going to run this real quick just to check it and make sure everything's okay. Highlight this and run it. 0.8891. Okay, good. So I'm going to run reliability on all of these really quickly. So all I'm doing is taking, so T mass is just going to be all of these. All right, so I'm just going to run this really quickly and see what we get. Uh-oh. That's not good. 0.56, that means we didn't do something right. Mastery Q2. Mastery Q5. Mastery 1 reverse. Mastery 3. Mastery 5. I'm trying to remember. Let me just check something really quick to make sure that these are all done properly. So I'm gonna run a cross tab on mastery. All right, so what I'm doing is this is low, right? So this indicates that something is wrong, right? Typically you don't want it less than 7. Now, I can't remember whether or not, well, let me see. Did we find in the paper that it was low? Let me see. Let me see here. Accuracy confirmed. Okay, we did that. No. Oh, these are not even the right ones. All right. So whenever you see something like this, right? Whenever you see a low Cronbach's alpha, typically you want it to be 0.7 or higher. So the fact that this is so low means that maybe something didn't go right with the coding when you have reverse coding. So I'm just going to check it. So mastery reverse 1. So I'm just going to check let's see, mastery 1 versus mastery reverse 1. So we're going to check that. Okay, so 1 is 4. 1 is 4. 2 is 3. 3 is 2. 4 is 1. Okay, so that's fine. That's fine. All right, so let's do the next one. So let's see, mastery 3. One and 4, 3 and 2, 4 and 1. Okay. All right, that's fine. So now let's go and do the next one. It may just be low, but you just want to check it. You just want to make sure. So mastery 4, mastery 4, 1 and 4. Seemed like nobody scored a 2 on this thing. Interesting. Well, I guess that's just the data. Whoa, 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 whoa. Okay, so here's where we have a problem. We got values here and we've got values here. So we've got to figure out why this happened. We've got to figure out why this happened. I knew something was wrong. So here's what happened. Let me just take you back through this because this is, how people in the data analytics world actually go through it. So you're going through your process, you're doing all of your checks. You see that you have a low reliability. That means the internal consistency of the scores is not good, right? Now, I had to reverse some scores, right? So that means that, okay, if I hadn't had to touch the scale at all and I just got a 560, it's just 560 because I didn't do anything. But I reversed some of the variables in the scale, and now I'm getting this low number. So whenever you get a low number like that, that means typically there's something wrong with the internal consistency of the scores, because like I said, you want them to be 0.7 or talked about, right? So in other words, if someone scores high on one and they should have scored high on another one, or they should have scored lower on another one, then that would be internal consistency if everyone did it. But this is showing low internal consistency. And the reason that is because we're coming down here. We've got people who scored a 3 on mastery question 4 are receiving a 4 on the mastery reverse code, and the people who scored a 1 are also getting a 4. So that can't be right. So I'm going to go back and I'm actually going to delete mastery 4 because I probably did something wrong in the code. So let's go, and that's why it's so important. Okay, so mastery, let's see, mastery 1, 3, 4, 6, 7. 1 is 4, 2 is 3, 3 is 4, 4 is 1. Ah, there it is. 1 is 4, 2 is 3, 3 should be 2, not 4. You see that? That's why I made the mistake. 1 is 4, 2 is 3. So in other words, it should be this. Where's my pen? If everyone sees where I made the mistake, type in a 1. If you don't see where I made the mistake, type in a 0. So essentially, it should be 1 to 4, 2 to 3, 3 to 2, 4 to 1. What I had was 1 to 4, 2 to 3, 3 to 4, and then 4 to 1. That wasn't right. So now you got 2 values going to 4, which is not correct. It should be 4, 3, 2, 1. So that's why, when you look at the data, you can see what the data is saying. It's like, oh, something went wrong. That's why I'm saying numbers in these tests, they can reveal so much information, right? So having gone through this, you're able to see how people in the real world can actually do this. We are not seeing anything you are not showing. Okay, got it. All right. All right. So now I'll say I'm going to fix that. 1 is 4, 2 is 3, 3 is 2, and 4 is 1. So I'm going to rerun this and fix it. And then I'm going to go back and run Cronbox Alpha again for mastery and see what we get. Because that was a red flag. When I got that point, that 560, that was a red flag right there that something wasn't right. That's why you always go through your checks, right? Because if you miss something, the numbers will tell you, something's not right. And then you go back and you can check. That's why following that workbook that I gave you, this one right here, this will save you. Trust me, this will save you if you follow it. All right. So, but I just know it in by heart. So that's why I don't really, Okay, so I'm going to go back. I'm going to run this again. And where is my score? 0.756. Okay, that's better. That's acceptable, right? So that's acceptable. So now we can go and we can run the other ones, right? So let's see. Reliability, mastery. So I'm going to highlight this. No, the other one is 1 to 5. That's fine because they're all the same. Copy. Another thing, using syntax is so much faster too. T-mast, total optimism. Let's see. So reliability for mast, reliability for life satisfaction. And then we're going to do optimism. Life satisfaction, mastery, and then optimism. And we're just going to take out commas. Is watching me do this helpful at all? I know we're a little behind, but if it's helpful, type in a Y. If it's not frustrating, just type in an N so I can know. 801. Okay, so that's good. That's good. So that means we're good there. And we just have one more. Life satisfaction. Okay, we got life satisfaction, mastery, optimism. What's the other one? Optimism, did we do that? Yeah, we did that. Optimism, total mastery. Oh, perceived stress. Need to do that. All right, so we got perceived stress. Take these commas out because in reliability analysis, it doesn't use commas, but in all the other ones it does. So it's got to be REV too. So REV, take out the commas. REV, take out the comma. REV, take out the commas. Okay, looks like we're all good. 5, 7, 8. Eight, 4, 9. Okay, good. All right, so we're good there. All right. Very good. Now we don't have to run descriptive statistics or anything like that. I liked how you problem solve. Yes. And that's what data analysis is. It's really understanding the numbers, right? Because all these numbers are telling us something. The lesson for me is the value of keeping the syntax. Yes. Very important. Oh my goodness, because you can go so much faster. And you always have a written record. People just go click, 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 click. And then if they ever mess up, they don't know what they did. So you can go back and you look, oh, okay, I see what I did. I see where I messed up. Always use syntax. That's my recommendation. Okay. All right. So now that we've done that, everything's smooth. That's fine. We've already done that. We did that last week. We did the reliability. Now where we are. Okay. So here is where we actually perform the analyses. But before we run the analyses, we have to check the assumptions of the data. Okay. So the assumptions basically, so they call them parametric assumptions, right? Each statistical test has certain parameters that must be met, generally speaking, in order for the test to yield accurate results. Okay. Each statistical test has certain parameters that need to be met in order for the test to yield accurate results. If that makes sense, type in a 1. If it doesn't make sense, type in a 0. Now, on this page here, it says perform test of parametric assumptions. These are the assumptions, and these are the tests. Let me just make it bigger. These are the assumptions across the top, and these are the tests along the bottom. And wherever, let me just make sure. Okay. And wherever there's an asterisk or star, that means that that particular test needs to meet that assumption. Okay. That particular test needs to meet that assumption. Okay. If that makes sense, type in a Y. If it doesn't make sense, type in an N. These are the assumptions across the top, and these are the tests. And wherever there's a star, that means that that particular test needs to be checked for that assumption. Okay? So we are running a bivariate correlation, a multiple regression, and a one-way ANOVA. Okay? So for a bivariate correlation, okay, we're going to put this bivariate. The assumptions that we have to check are normality and linearity and homoscedasticity. Okay, so what do those mean? So normality means that the distribution of each of the variables needs to be relatively bell-shaped or normal in shape. Okay, so basically, where's my pen? Okay, here we go. All right. So basically what we're saying here is that a normal distribution looks like this. I mean, it's prettier than that, but it needs to have a relatively bell-shaped curve. If that makes sense, type in a Y. If it doesn't make sense, type in an N. Okay, great. All right, so that's one assumption. The next assumption is, for the bivariate correlation, is that there is a linear relationship between the variables, meaning we're trying to determine if there is a linear relationship, if hours of sleep is linearly related to exam score, no, this is not even the same thing. If it's not hours of sleep, if back here, if age is related to optimism, life satisfaction, and perceived stress and mastery. There needs to be a linear relationship, okay? So that means that we have to run a scatter plot, okay? A scatter plot. So let me just put these here like so. Okay. All right. Okay. So that one's going to, we'll call scatter plot. And the scatter plot is also going to tell us if the spread of the data is wider at one end than it is at another. So let me explain. Okay, so first thing let's do is let's check for normality. Okay, so for normality, we're going to go, to analyze, descriptives, and then explore. Okay, then we're going to put the variables that are going to be in the correlation. So the first one's age, and then we've got total mastery, total optimism, life satisfaction, total mastery, total optimism, life satisfaction. Did we compute perceived stress? Let me check. Did we compute life satisfaction? Compute. Okay, so we haven't computed perceived stress. Okay, so let me just perceived stress. Okay, so we're going to compute this. So we're just going to grab this compute code. Bring this down here. And then we're going to bring perceived stress. We did reliability for perceived stress. So we're going to do this. And we're going to put this in here. And then we have to put in the commas. So, comma, 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 comma. Okay. We're going to highlight this and we're going to run it. And then we're going to check it to make sure there are no missing values. Uh-oh. Okay, so let's do this again. Oh, because I didn't change the name. Because what I did is I looked here and I'm like, hey, where's perceived stress? And there's no perceived stress because I didn't change the name when I copied the code. Okay, so it should be PSS tote, right? So I'm going to do that. See something. So now I've got to go and rerun life satisfaction because all the life satisfaction total scores have been replaced with perceived stress. So let me go back up here and run life satisfaction total. Okay. And then I'm going to go back and change this to perceived stress, PSS total. Okay. All right. So now we're going to come back and just make sure we got everything. Perceived stress total. Highlight this and run it. Okay, we're good. All right. 12 to 43. All right, we're good. All right, now, so we're going to check for the assumption of normality. So we're going to go to descriptives. We're going to go down to explore. So we want to explore the health of the data. So when you think of explore the health of the data. So let me just reset this. So we're going to put in age, right? We're going to put in optimism, life satisfaction, perceived stress, and mastery. So all the scales. So age, perceived stress, total optimism, total mastery, and life satisfaction. Life sat total. Okay. Then we're going to go to plots, right? Normality plots. We want normality plots. Okay. Normality plots. I'm going to uncheck stem and leaf, and we're looking for normality plots. Okay. We're going to click continue, and then we're going to click paste. And this is going to tell us if the data is normally distributed for each variable. So this output and what we're looking for is called the Shapiro-Wilk test. The Shapiro-Wilk test. Okay. So what this is saying, the Shapiro-Wilk test tells us, is there a statistically significant difference in the distribution of age from the normal distribution? Is there a significant between the distribution of scores in age and the normal distribution? If it makes sense, type in a 1. If it does not make sense, type in a 0. Okay, that's what this test is asking. Is there a significant difference between the bell-shaped curve and the distribution of age? All right, so now let's go and look at age. Let's see something here. Histogram. That's what I should have. Okay, so let's do that again. Let's click continue and click paste. Now, what I unchecked stem and leaf, but I didn't check histogram. Histogram is the shape, right? Because I want you to see the shape, and that's very important. So we're going to click continue and we're going to click paste. And then I'm going to close all this out and I'm going to rerun it with the histogram. So I'm going to take this one out. I'm going to rerun it so that you compare the histogram of each variable to the normal distribution. Okay. All right. So we're going to come down here. So this one says there is a significant difference between age and the normal distribution. Well, here is the distribution for age. Okay. Here is the distribution for age. This goes like this. That's different from the normal distribution. There's a significant difference between the normal distribution and the distribution of age. If you can see that, type in a Y. If you can't see it, type in an N. That's what this is telling us. And I'm just giving you the visual of what it means. Okay? Got it. Got it. Now, so now let's go down to the next one. We're looking at PSS total and the normal distribution. So what was the number up here? 0.019. It wasn't as bad, but it's still significantly different, right? So we've got this, and we've got this. Now, the reason why it's probably significant is because it might be a little taller than it should be. Okay, it might be a little taller than it should be. All right, so that's the second one that is significantly different from the bell-shaped curve. Now it doesn't look like it, but it technically, statistically, it is. But don't fret, I've got a solution. So now we're going to go down and we're going to look at the next one. Okay, this one is different as well because, ooh, that's not what I wanted to do. This one is different because it goes like this. Okay, that is significantly different than the bell-shaped curve. If you can see that, it's very different, right? If you can see that, type in a 1. Okay, if you can see that it's different, type in a 1. Excellent, excellent, right? So then we're going to go down to the next one. Again, this is what we call, so here, let me just say this. This one here is what we call a positively skewed distribution. Okay, this is a positively skewed distribution because wherever the tail is, if the tail is sliding to the right, where the numbers are going higher, we call that a positive skew. It's skewing upwards, meaning as the numbers increase, that's where the skew is. So this is a positively skewed histogram. Okay, a positively skewed distribution. Positively skewed distribution. Okay, positively skewed distribution. All right, so then we go down to the next one. This is not positively skewed, it's not negatively skewed, it's just a little tall. Okay, this one is leaning towards the left, so we call this a negatively skewed because the numbers are skewing to the lower end. So this is what we call a negatively skewed distribution. Okay, because it's negatively skewed, it's skewing low towards smaller numbers. Negative meaning skewing towards smaller numbers. Okay, if that makes sense, type in a Y. If it doesn't make sense, type in an N. Okay. All right, so now we're going to go down to the, this again is another negatively skewed. It goes up and then it's sort of skewing this way. So this is another negatively skewed distribution. All right. Okay. And then the last one, oh, this is interesting because what it does here is it goes up and then it comes down. It's a really strange looking distribution. It's not normal at all. It doesn't have a clean bell-shaped curve. So this is it's almost got a negative skew because the peak is here. And then it just goes downward. So it's a slightly negative skew. Okay, slightly negative skew because the distribution is slanting down this way more than it's slanting this way. So it's skewing this way. Okay. All right. So we see that there are violations in normality. But if you look on your sheet, right? If you look on your sheet, what does it say? It says that robust explanation test chosen. The central limit theorem, the theorem of large sample sizes. If n is 30 or larger for your sample or the subgroups are at least 15, you can still run parametric tests to obtain reliable results. And these are the references, okay? And basically what that's saying is that let me just explain it to you. There is a video where I talk about the central limit theorem in the pre-workshop videos. And basically what it's saying is that even if the distribution is not normal, correlation, regression, and ANOVA are still strong enough to counteract the negative or positive skew, okay? And it's called the central limit theorem. These are what we call robust tests. And a robust test is a test that says, hey, even if there are violations in normality, a robust test will still give you accurate p-values that are within plus or minus 0.03 of the true p-value. This is what we call a robust test. A test is robust even if the violations occur, because the central limit theorem basically says that, hey, we are going to be within plus or minus 0.03 of the true p-value. So correlation is robust. ANOVA, or what they call general linear model, is robust, and regression. Linear regression is robust, okay? If that makes sense, type in a 1. If that does not make sense, type in a 0. Basically, these tests, even if they're violations in what we saw, right? Even if they're violations, we can still run the test because they're so powerful that they will still be able to detect significant relationships and significant differences between the groups. All right. All right. So now let's see correlation. Another thing we want to test is linearity. Okay. So let me just show you how we do that. Now, to test linearity, what we do is we run scatter plots. So we go to, let me just show you. So we go to graphs, legacy dialogues, and then scatter. Okay. Click on simple scatter. And then what we're going to do is we're going to put in age in the Y, because, you know, we're going to keep it there. We're going to keep, because everything's going to be run against age. So age, and then we're going to do life satisfaction total. That's the first one. Okay. So we're going to highlight this and we're going to run it. Now, here's what we're looking for. We're looking for linearity, meaning we're looking for a pattern that does not look like this or that does not look like this. These are bad. These are what we call curvy linear patterns. We want straight patterns. Okay. Now, one of the things that we can do is double click this, double left click, and then hit this line that says fit line to total, and it'll show what the line is. Okay. It'll show what the line is. And this line right here, it's almost flat, but it's still linear. In other words, this pattern does not have a curved shape. Okay. If that makes sense, type in a Y. If it doesn't make sense, type in a 0. Right? We don't. So in other words, let me just demonstrate. If we saw a pattern that looked like this, that would be bad. Or if we saw a pattern that looked like this, this would be bad. But this is just a blob. And that's fine. Okay? That's fine. Now, something else I want to show you. Another thing we're testing for is homoscedasticity. And homoscedasticity means the spread of the data is roughly the same across the entire distribution of plots. So in other words, we want something that's relatively rectangular. The plots fit in a rectangle. We don't want something that looks like this. Right? Where you got plots, excuse me, and then it gets skinny in the middle and then wide at the end. Or you have a plot that's wide at one end and skinny at an end like that. These are what we call violations in homoscedasticity. Homo means the same. We want the data, the spread of the data to be relatively the same throughout the entire distribution. And that's essentially what we have. It's roughly the same, right? It's roughly the same. So we have no violation of linearity. We have no violation of homoscedasticity. If that makes sense, type in a Y. If that does not make sense, type in an N. Okay. All right. Now, so now let's go and do the next one. Am I still online? If you can hear me, let me just make sure that people can hear me. If you can hear me, type in a Y. If you can hear me, type in a Y. Okay. All right, great. All right, great. All right, so now we're going to the next one. Graphs, legacy dialogues, and then scatter dot. Scatter, and we've got age in there. So now we're going to do the next one, which is total optimism. Click paste. Highlight this and run it. Okay. Now this one's interesting. This one is interesting. Okay. Because it seems to go something like this. Okay. It seems to go something like that. Okay. There's no violation in linearity because the distribution is not curvilinear. It's not curvilinear, but it doesn't appear to be uniform. Okay. It doesn't appear to be uniform. Okay. But we can check for that. All right. We can check for that. And we can go to analyze general linear model univariate. Okay. We're going to put age into the dependent variable box. And then we're going to put total optimism into the covariates box. Covariates are always continuous. Okay. Then what we're going to do is we're going to go to, let's see, is it plot? Oh, not that one. Options. Yes. And what we're going to do is we're going to test for heteroscedasticity. We're going to use the modified Breuer-Pagan test and White's test. Okay. And basically what we're asking here is there a statistically significant difference between a homogeneous distribution and our distribution? Okay. A homogeneous distribution and our distribution. So we're going to click paste. Highlight this and run it. Okay. So yes, there is a significant difference between a homogeneous distribution, a homoscedastic distribution, and our distribution. And we saw that, right? We thought we saw that, but we wanted to check to make sure. All right. So what do we do? What do we do? It's okay. We're just going to run it. We're still going to run it. We have to make a note that there appeared to be a violation in homoscedasticity. Okay, we're just, because that's a limitation of your study. Okay, that's a limitation of your study. Now, there's an article here by this guy. I put it inside your sheet. There's an article by a guy named let's see. I think it's this one, Poston. Robustness of statistical methods and non-parametric. Yeah, I think it's this one, this Poston. Violation. So I believe it's either, oh no, I think it's the Schmider all. Yeah, I think it's Schmider et al. They did simulations. They did computer simulations with data, and they tested various sample sizes, various distributions, homoscedasticity, and all that kind of stuff. That article right here, this one right here, if you want to, justify running tests, even when they have violations, use this paper, because they've done probably the most thorough work on the robustness of the correlation, the ANOVA, and the regression of anyone. So that's definitely a paper you want to have in your arsenal. Okay. All right. So now let's see. We're going to go and we're going to run graphs, scatter, and then I'm going to take total optimism, total mastery, click paste, highlight this and run it. This one, no violation in linearity. It's a little strange. It's a little strange, but I think it would pass. Let's test it and see. Let's test it and see. So analyze general linear model univariate. and then total mastery, right, in covariates. And then we go to options and we select modify Breuer-Pagan test and the White test. Click continue. And then we're going to click paste. Highlight this and run it. Oh, we're good. We're good. So even though we had this funny shape, right? Even though it was a little funny, there's no significant difference between a homoscedastic distribution and that distribution, okay? Because these are all greater than 0.05, right? Less than 0.05 means that there's a significant difference between your distribution shape and a homoscedastic distribution shape. So this says there's no difference. So that's great. All right, so we're good there. All right. So now we go to the next one, the final one. And yeah, T-mass and perceived stress total. Paste. Highlight this and run it. Yeah, this one looks fine. There's no curvy linearity, and these are all pretty much uniform. Okay, so we're good. Now that we've done this, we can run our correlation analysis. All right, now we can run our correlation analysis. So the correlation, we go to analyze, correlate by variant. We're going to put age. So the variable that you're comparing to all other variables is going to go in first. So we're going to put age in first. Life satisfaction, total optimism, total mastery, perceived stress. Okay. Now, if you have severe violations, so we found that there was one test that had a violation in homoscedasticity. Whenever you have violations, you're going to run the Pearson test and you're going to run the Spearman rank order non-parametric correlation. The Spearman rank order non-parametric correlation. So you're going to run both of them and you're going to see if you get different results. Okay, click paste. Highlight this and run it. All right, so Pearson correlation. We see, let me just do this really quick. So is age significantly related to life satisfaction? P-value is 2.35. So the answer is no. Is age significantly related to total optimism? Less than 0.05. All right. Is age significantly related to total mastery? 0.05 or greater? No. Okay. Is age significantly related to perceived stress total? Here, this what we call tail. Less than 0.05, yes. So what does this mean? This means here it's significant. So then we go here. So this is step one. And then we go to step two, which is to look at the Pearson correlation. So the Pearson okay, hold on. I think somebody's asking me something. I thought it was the star that determines the relationship. The star is just a reflection of the number, right? So 1 star means it's significant at the point level. 2 stars means it's significant at the 0.01 level. But here's the actual p-value right here. Okay? So the stars simply reflect what the numbers are. So this one has a star because it's less than 0.05. This one doesn't have a star because it's 0.05 or greater. This one doesn't have a star because it's 0.05 or greater. The sig2tell is really the p-value. That's all that means. So it's the p-value that determines. So this is the p. Let me get this, make it smaller. So this is the p. This is the p-value. This is the p-value. And this is the p-value. The star just indicates what the p-value is. If that makes sense, type in a 1. Got it. Okay. So then once you look at the p-value or the star, different. Because sometimes some softwares don't use stars. They just use the p-value. So then, okay, so let's look at the ones that are significant. So we see here that it's a 2.212. Okay, so basically, let me just show you something really quick. So if the line is going like this, that means it's a positive correlation, meaning as one number increases, the other number increases as well. So that's what we call a positive. If it's a negative correlation, okay, then that means that you have a situation where as the numbers increase on one, they actually decrease on the, okay? As numbers increase here, they decrease here. So this is 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay? So this is a positive 2.235. So that means it's a positive correlation. This one is a positive 0.422. So the larger the number, okay, so this goes from 0 to +1 as far as the correlation coefficient. This goes from 0 to -1 correlation coefficient. Okay? So the correlation coefficient here is minus, whereas the correlation coefficient here is positive. So this one is minus. Oh, no, that's not significant. Hold up, let me go back. So this one is. So this means that as age increases, perceived stress scores go down. So basically so let's say this is age and this is perceived stress. So as age increases, your scores on perceived stress are going down. So the older you get, the less perception of stress that you receive. Okay. Now, for this one, it's positive. So that means that as age increases, your scores on optimism also increase. So this is age and this is optimism. So as age increases, so does your scores on optimism. If that makes sense, type in a Y. If it does not make sense, type in an N. Okay? So that's essentially how you do it. All right? So we went over a little bit. So tomorrow we're going to run the regression and the one-way ANOVA. And we should be able to finish that with no problem because we'll have the entire hour. Okay? Does anyone have any questions? If you have a question, type in a Q. If you do not have a question, type in an N. Okay. I appreciate your patience. As I went through this, and I actually had to start over from scratch, so you actually saw me go through the entire process until we were able to. So basically, tonight, I did everything we did over 5 days in like 20 minutes. And I wanted to do that. I didn't mean to do that, but you were able to see how fast this can go once you become very comfortable with the data and you understand what you're looking at, what the numbers are telling you, and so on and so forth. So, and I also want you to appreciate that I take my time when I'm going through all of the steps with you, right? So something that takes me 20, 30 minutes, I'm going through with you in 5 days so that you can get it. Does that make sense? That's how methodical I am when I teach, because I don't assume you know everything. I break everything down into micro steps, even though I can do it in, 20, 30 minutes, but I break it down and I take my time. Okay. All right. So tomorrow will be day 7, and we will continue where we left off here, and we will start at 8 o'clock. Thanks for that. I appreciate the minute steps. You're very welcome. You're very, very welcome. Very, very welcome. Because that's how you learn. Because if you can break down the steps like that and you just keep doing them over and over, you'll understand. You'll definitely understand. You're very welcome. Thank you. Thank you. All right. Okay. So thank you. I appreciate your time, and appreciate all the effort and you putting up with me. And I'll see you tomorrow. Okay? Enjoy your evening.